Okay, so hi everyone. My name is Jonathan Ozik. I am a computational scientist at Argonne. I have joint appointments at UChicago and Northwestern. And today's talk will be a joint one with Valerie. And we'll be talking about developing distributed high-performance computing capabilities of an open science platform for robust epidemic analysis. From here on out, it's just OSPREY. Okay, the name of the platform is OSPREY. And this is work done with a lot of people, some of whom are in this room, some of whom are here virtually, and others I'm not sure why they're not at Parcel Fest. So the outline, brief outline, I want to motivate why we thought of creating a platform like this. And then we'll do two examples of, let's see, am I hiding it? We'll do two examples that of work we've done that intersect with this festival of Parcel and Globus Compute. Okay, a prototype OSPREY architecture, and then Valerie's going to tell us about data streams as a service, or DSAS. Okay, great. Funding acknowledgements. Before I forget, thank you, NSF, DOE, the FACTS program here, and NIH. Okay, so why OSPREY? So think back to the tumultuous early days of 2020. There's a great article if you want to relive that harrowing or frenzied early weeks, 67 Days to Lockdown on Chicago Magazine. They interviewed a number of people, stakeholders that were involved in the lead up to Governor Pritzker's stay-at-home declaration here. And so they interviewed these folks, and the former commissioner, public health commissioner, Allison Arwady, mentioned this, that Argonne National Lab built what's called an agent-based model specifically for Chicago that predated COVID and mimics the movements of its 2.7 million residents. All the gyms, schools, and businesses are built, etc. So pretty early on, we connected with them to start thinking about using that Chicago model for COVID. So for our perspective, it was a great use of our previous work in doing infectious disease modeling. But we were doing that at academic scales, right? 6 months, few years to get results. And then we had to pivot to a pandemic prevention, pandemic response timescales, which are weekly. So very early on, we had to figure out how to utilize large compute quickly and efficiently. And so we were not alone in trying to do this. As you probably know, during COVID, individual research groups worked independently, and they tried to exploit advances in HPC, data management, MLAI, and automation methods. And this was to develop and to calibrate, to modify, verify, and validate their epidemiologic model. Okay, this is an issue because it required large amounts of heroic and, importantly, overlapping work. And the bespoke solutions that they came up with risk lacking robustness, security, scalability, or efficiency. So that's one. That's the computational platform capabilities. The second is that we were dealing with heterogeneous, changing, and incomplete data that required complex integration across diverse and novel surveillance signals. So this created significant challenges for use in epidemiologic workflows. And so OSPREY sought to lower the barriers to automate these types of analyses on HPC and cloud resources. So the first part of the talk, I'll speak about the prototype OSPREY architecture, which addresses the first point, and then Valerie will speak about DSAS, which speaks to the second point. Whoops. Okay, so we have a bit more time, hopefully. Okay, great. Great. Thank you. I don't know why I'm wasting this time talking to you, but yes, this is great. So, okay, so we built a prototype OSPREY architecture, and we go into depth as to the requirements we came up with for such a general architecture, and we provided this image of a prototype version of it. So in brief, this includes a model exploration module, which dictates the logic of this workflow. There's a function as a service task distribution. There's eMuse, which is our model exploration, generic model exploration framework. There's scalable worker pools, and then their data sharing by things like proxy store. And collectively, they provide us the ability to robustly and securely coordinate epidemic, but not obviously not just epidemic workflows across distributed ecosystem of heterogeneous remote resources. So back to the meat of this. So we developed a task API that include remote workers, service monitoring, coordination. And Globus Compute allows us to reach into a variety of HPC resources and start up these services and tear them down as necessary. So basically on demand. We also have this concept of worker pools that are tuned to specific types of tasks that will run tuned also in terms of which kind of hardware they will be run on. And so we have this ability to provision them, monitor them, tear them down as we need them on demand, kind of speaking to a little bit of what Logan was saying in his talk. And we do this with a combination of Globus Compute and SciJ. And then importantly, we have these secure and long-running access to from the model exploration algorithm to create tasks, and also from the model exploration algorithm or other client code to analyze the results that come by. This also allows us to create interesting asynchronous workflows that allow us to do things like deprioritize or increase the priority of a task that hasn't been run yet, but now we know is very important to do or less important for deprioritizing. And so we provided a simple example of tasks being reprioritized and worker pools being launched on demand based on internal logic of the workflow. Okay, Valerie, go ahead.
So I'll talk rather quickly about DSAS. This basically focuses on extract, transform, load, as well as storing and sharing of the data. It's currently very much in prototype stage, so things might change from here, very likely. So this is kind of what it looks like. As a whole, you have a user that can specify a data source. This can be any kind of open data CSV, or it could also be a private one. And they give information of how to validate the data to ensure that it's functioning properly, as well as how to modify it to be used in analysis workflows. And also they'll provide a timer such that our service will go and refetch the data. So this is the data stream aspect of it. So first you submit your source, a timer gets launched at periodic intervals, which at that, once it gets triggered, it launches a Globus flow that runs validation and that fetches the data, runs validation and modification of it. And if all checks out, it will store it in a Globus Connect server. And at this point, users over here can query the data or can query the service to see what kind of sources are available, and use a Globus Connect or a Globus transfer to run that or to use the data within their analysis pipelines. And then they can restore that or put their artifacts back into the service, and will track provenance of how the source data was modified, as well as how their analysis workflow was executed. And then here is a very rough example of how we will hopefully, or how this can be integrated into parcel functions. So first, the source will not, the adding of the source will actually be done outside via CLI. This is just an example of how you can use it. So you specify a name for the source, the URL of where to fetch it, the timer update, or how the timer interval rather, and then your validation function. You can also add the modifier function. These are actually Globus Compute UIDs. And then yeah, within a parcel function, a user will be able to fetch that data given an ID or the name and also a version for that data. And finally, we'll look at how users will be able to store that data, to store their analysis artifacts within the service. That's it.
So how exactly, what determines what gives like a task prioritization over another task? Like what parameters are used to determine that?
That's really up to the algorithm. So we've done a case from the simple example where a surrogate model is telling us that these parts of the parameter space are less important now, and if they haven't run yet, then don't worry about those other ones that are look to be more important. So that's a simple example.
So I've got a question about the task deployment. Do you use two different Globus Compute tasks? One that starts up emus on the remote system, and then another that runs a task? Or is it just the one that starts up emus, something else?
Yeah, so that's a good question. So they're two different. The idea is that you can have an emus service and database on a resource without any workers running at all. And then separately, we can then provision workers as needed on that resource. And the idea here is that it's not a generic worker pool. We can create a generic worker pool, but in most of our use cases, we find that the worker pools that we create have, very particular requirements to run the tasks efficiently. For example, our COVID model required specifically, tuned allocations, libraries, etc., compilations and whatnot. So we're already going to the trouble of doing that. So we already define the types of worker pools that can be launched on a resource.
Okay, but when it comes for those worker tools to receive a new task, does that come via Globus Compute or the emu service?
That comes from the emus service. Yeah,
okay.
They query they query the emus database for that.
I see. Thanks.
You're welcome. Question back.
Yeah, about just the algorithm that prioritizes different tasks.
Yeah.
Does that have any optimization algorithm that follows it? Can you choose that as a?
Yeah, it's very generic. So the example that you'll see in the paper is an example that actually we got from the Logan and Colmena's documentation. It's a general purpose toy example where you fit a surrogate model based on the data that you've already received, and it'll just direct you in which points are better than others to evaluate. Yeah. But it's generic. Yeah, you could do it by how long something takes to run, for example, too.
Cool.
Overstayed our welcome.